Hi, welcome to the Bioinformatics chat. This episode is devoted to this year's Bioinformatics contest organized by the team from the ITMO University and the Bioinformatics Institute in Russia. And today with me are Alexey Sergushichev, who is one of the organizers of the contest, and also Gennady Korotkevich, who is the first prize winner of the contest. To start with, I usually ask my guests to introduce themselves. We already met Alexey last year. I think it was episode number 18, so you can go and listen to that episode to hear about Alexey. But Gennady, tell us a bit about yourself.
Yes, sure. So I'm a student at ITMO University in Russia, which is an organizer of this contest. I take part in a lot of programming competitions. I occasionally win some of them. And, Bioinformatics contest is different from most usual programming contests, but it was still very interesting, so here I am.
So you are primarily known as a very successful competitive programmer, but what is your relationship with bioinformatics? Is it one of your interests, or is it just like another fun competition for you?
Oh, well, 50-50, I'd say. I'm mostly interested in the informatics part of bioinformatics naturally. So, in fact, my master's thesis was under Alexey's supervision. It was connected to bioinformatics, but again, I was mostly doing the informatics part of that. So yeah, I guess I'm just interested in the informatics part of many things if they have this part.
Right, that makes sense. But you're a student, and what do you study? Is it just computer science department, or?
Yeah, it was just computer science, yes.
And of course, congratulations on your stellar performance in the contest. Not only did you get the first prize, but you got it with a huge margin.
Thank you.
What did you think about the contest? What were your impressions?
Yeah, I guess what can describe this contest the best for me was the fact that I arrived from Japan the day of the contest, and then I wasn't sure I was going to take part at all. But when I read the problems, I found them very interesting, so I just had to go into the contest. And basically, I didn't sleep too much because I didn't have enough time otherwise. But I was so excited that I just continued to work on the problems instead of going to sleep. So I guess that says more than words.
Yeah, that's a great compliment to the contest. And in Japan, were you participating in another competition?
Yeah, that's true. It was. It's called Headquarter World Tour Finals. It was organized for the first time, and yeah, it's a programming contest, not related to biology. I was there like for several days and just came back right then.
You've participated in a countless number of these contests. What do you experience? Do you get anxious, or are you used to it? What kind of emotions are you going through when you're participating?
For sure, I'm very competitive, so I usually get anxious, but it depends. Like, mostly I try to stay calm, and when you have participated in a lot of contests, I guess, yeah, you get used to it, but every time it is something new, some new experience. So,
Alexey, what were your impressions of this contest? What stood out to you?
Well, first of all, it was, from our perspective, it was pretty great technically. So as you can remember, like in the first one and the second one, there was some problem with tests, so we had to fix a few things during the contest. So this, for the third time, we finally got it done, almost perfect. So there was some clarification issues with problem statements, but otherwise technically it went fine. Like with Vitaly Aksonov, who is another main co-organizer of this contest. So we and Bioinformatics team, we looked thoroughly on the contest table and waited and asked people around us whether the Gennady will be participating or not, because like by mid-contest, I think, or like after 6 hours or so of the contest, or the thought of the contest, he was not there.
Yeah, I was flying.
Did you not have Wi-Fi on your plane?
I didn't bother. I wanted to sleep more during the flight. But then...
Yeah, so after this, about third of the contest, another our student, Nikolai Budin, was on a first or second place, I believe. So we rooted for him. But then, when Gennady arrived, we still rooted for Nikolai. But when so basically when so with Vitaly Aksonov, we stayed to ask to reply for the questions. So when I went to sleep for a while around midnight St. Petersburg time, so Gennady was more or less at the end of the table. Like he started solving something, but then when I wake up like 4 hours later, so he was like at the second place after Koля, after Nikolai. So there was some competition, but then like after several more hours, so he went ahead. Yeah, but so it was kind of dramatic, but then Gennady won it.
So let's go through the problems, and we will start with the qualification round, which lasted 1 week. It was in the beginning of February. And the first problem was called Bees Population. The author was the jury, and whatever that means. And the tests were by Grigory Shavkoplyas. And the essence of the problem was that you have a population of bees, and their population number is changing according to a certain law, basically a quadratic function. So the population at the next day is some coefficient times the population on this day minus some other coefficient times the squared population on the previous day. And a nice touch to this problem is that this is actually a very realistic law. So at first it appears contrived because you're just given this quadratic formula, and your first thought is, well, they just came up with the quadratic formula just because it's a simple formula to analyze. But actually, this corresponds to a sort of well-known logistic growth function in population dynamics. So that's nice. Although it wasn't explained, I think it would be more interesting if this was motivated a bit. But the task was to calculate the limit of the population. So if you let this process continue for some time, does it converge to a certain population level? And if so, then what is that limit of the population?
So first of all, I would say that what the jury means. So that basically for the qualification round, we tried to think about to make a problem, very pretty simple one, like that can be solved more or less with a formula. So we discussed a lot what could be done there. So we Googled a lot. So finally we found this really nice population model, which is very simple on one hand and can be solved with a formula. And well, it has pretty decent biological background. So that's why we have it, and that's why it's jury. So it was highly discussed inside the team, inside the jury team.
How big was the jury this time?
Well, so there was a lot of people involved. So you can find it on the contest website. So actually, I even don't know the exact number. I guess it's around 12 people total. And so basically we, not with all the people, but with some team, we sit around and chatted and tried to make a problem for this specifically. And actually, just to make people understand like how the whole process works of creating the problems. Basically, we first everyone from the jury and from our friends, we ask people to submit the ideas of the problems, and then we discuss how they can be solved, how hard they are, how suitable they are for contests, and so on. So we discuss it inside the team, and there we try. So at some point we understood that we don't have this simple problem for the qualification, and we then found this particular problem.
Yeah, and so you can solve it with a formula. So you have to carefully analyze like various edge cases, but the limit, if it exists, it is a solution to this quadratic equation. It's the intersection, one of the intersections of the line y equals x and the parabola. And one of these intersections is always 0. So that's always a possible limit, not necessarily the limit. And again, depending on the values of the coefficients, there may be another intersection points. And then you have to draw that. That's how I did it. I just drew various cases and what the limit is in each of them. But I also heard from my friends that they would just run the iteration for like million iterations, would run this process and see whether there is a limit.
Yeah, so that was one of what we also tried to achieve, that it can be solved with an iterative process, at least in some cases when it converges nicely, but not in every one of them. So I guess like for this, so there is bifurcation process, and for most of the cases it converges fast enough so that you can run iterative process and get a pretty nice value. But for some initial values, you just cycle a lot until it converges. So there you have to use the formula.
Yeah, okay. So just for statistics, I went for iterations because, well, I guessed it should be solvable by quadratic equations or something like that, but I was a bit lazy then, and I just ran the iterations. But with iterations, you have a problem that you have to determine if there is actually a limit, because like if you just run the iterations, then like you have to have some condition about the limit, right? But if you just run the iterations like for 10 million times and just output what you have, then I think you actually pass like 45 out of 50 test cases, which is good enough. Like you get almost all points for the problem. But then I think that I actually like considered a couple of cases by hand or something like that, and saw that I could get the remaining cases accepted as well.
That's pretty cool to hear from the winner that he used the simple iteration method. So
nice.
I guess there's no shame in it.
Yeah, of course. Like you're welcome to use whatever method you have in mind, right?
Sure. So the second problem of the qualification round was called sequencing errors, and the author is Alexey, and the tests were by Dmitry Yakutov. And in this problem, you have a circular genome of a certain length. You're not actually given a genome. You just assume you have a circular genome, and you try to sequence it. So you have a certain number of reads, and the reads all have a certain length. And there is a known probability of making a base calling error at each position in each read. And you have to calculate the expected number of positions with incorrect base calls. So you're not given any sequences in this problem. It's not that like you're given the actual genome or the reads. You have to, in your mind at least, you have to simulate an infinite number of sequencing runs where you sequence a circular genome, and then the base calling is done by consensus. So you sort of assume that all the reads are perfectly aligned, and then you calculate, at each position you take the most frequent nucleotide, or when there's a tie, then you pick randomly among those nucleotides. And given this process, the question is to calculate the expected number of errors. And I like this problem because a little bit of mathematics here goes a long way. So, for example, the first thought that I had when I read the problem statement was that it's really complicated because the error rate at each position depends on the sequencing depth at that point. So basically how many reads cover that position. The more reads you have, the less likely you have an error. And of course, the depth is correlated between the neighboring positions. So if at a certain position you have a very high depth coverage, then at the neighboring position you also have a high depth coverage. So you have this correlation structure, and it's really not clear how to analyze that. But then if you think carefully, right, what you're asked is the expectation, and expectation is linear. So you don't care about all these correlations, and you're just interested in, so you can consider one site in isolation and calculate the probability of an error just for that site, and then multiply that by the genome length. So that at least simplifies the problem.
I think it was the important step. Probably it was necessary to make this step. I'm not sure if you can solve it without this.
Yeah. So I guess, again, on the develop problem, so some people develop problems and some people develop tests and solutions. So being author of the problem, I don't know, I don't have a particular practical solution for it. But the idea here was that indeed, so there are actually two kind of tests, actually four kind of tests. But in each type of the problem, the first couple of tests can be solved by simulation. So it's the relative error is not required relative error is not that high. So that's our idea, was that people can just simulate the results, simulate the sequencing. But then for the most of the test cases where you have to have relative error of 10 to the minus 6, there you have to use this linearity of the expectation, and then you have to practically get the probability of the error. And actually, I also like this problem a lot because I came up with it with our students. So we discussed with our bioinformatics students. We discussed different sequencing technologies. So Illumina sequencing, nanopore, Sanger, and so on. So they obviously have different error rates and different lengths of the reads. So and the different prices per nucleotide. So there was a question from our students. So what would be the best sequencing machine to use, in any particular case? So how can you compare between them, having some budget or some library depth and so on? So, and because the answer is not that trivial, that's how basically I came up with this problem. So it's nice that it's both appears from very practical results, from very practical questions, like which sequencing machine you have to use in each with a particular budget and particular genome and particular library depths and so on. But it also involves pretty nice probability theory that you have to use to solve it.
I guess it's good to know that this problem is indeed pretty, I don't know, like real life connected. But, well, the solution is, I think I can go through the solution a bit.
Please do.
So this is kind of a combinatorics problem, in fact, like for the probability part of it. So basically for each position, like you said, we have to calculate the probability that we have an error in this position. And basically what we can do is, like since we have, at least in the hard case, we have 3 types of errors. So each parameter can be replaced by one of the other 3 with equal probability. We can iterate over the number of mistakes of the first, second, and third type. And if we know these numbers, then we can calculate the probability that these mistakes do happen. This is some kind of basic combinatorics, I'd say. So it's usually studied, I guess, in the university in the probability course. And then, so you just sum up the probabilities that correspond to actual mistakes of the majority choice. So that we just, for each case, we find the probability and then we sum up the probabilities of cases which we are interested in. Basically.
Right. So given a certain coverage of the position that we're considering, so we're considering a single locus, and we iterate over possible values of the coverage. So how many reads can cover this site?
Oh yeah. That's the first thing to do, right?
And out of that number, you iterate over all possible partitions. So how many of these are A's or C's or T's or G's? And for each combination of the 4 numbers, you can calculate what the eventual base call is going to be.
Yeah, that's true.
Yeah, but the problem is that the number of combinations gets pretty large, right? So you have to optimize it so that it runs in a reasonable time.
Yeah, the idea is that you don't have to try all combinations. Like if you have one read which reads A and the other one reads C, and the other case is the first read reads C and the second one is A, you don't have to consider these cases separately. But instead,
right, you consider just the partition.
Yeah, but
of
if
this
you have
number.
the partition, then if you know the partition, then you can actually quickly calculate the number of ways that you can get this partition, or more, it should be more correct to say the probability of this partition. So this one is just calculated with a formula.
Right,
so
but did you iterate over all possible partitions?
Yeah, I did. Actually,
okay.
It's not slow. Yeah, the cases. I think the cases were quite small. Yeah, I think the largest case had 150 reads. So we have 150 to the 4th power.
Yeah, that's interesting. Yeah, so I made an optimization. I don't know, maybe it was a premature optimization. I don't think I tried the straightforward iteration. One reason is that I don't know, maybe this is a bad strategy, but I usually don't look at the specific tests. So I just assume that they're gonna be huge. So I try to implement like a solution in such a way that I can just run it on all the cases and collect all the points and just, you know, as opposed to relying on the specific values in the test or specific test sizes. So one optimization I came up with is that so let's say you iterate over all possible values of how many A's you got at this site, right? So let's say you have those 150 reads covering this site, and you iterate over, there can be 0 A's, 1 A, 2 A's, 3 A's, etc., up to 150 A's. But most of these are very unlikely. Just because of the probability. So at each step, I actually calculate the quantiles, because this So the joint distribution is multinomial, is known as a multinomial distribution, where you have a fixed number of, let's say, nucleotides, and you partition them into 4 classes, into A's and C's and T's and G's. This is a multinomial distribution. But you can also iterate one by one. So first you iterate over all the A's, and all these marginal and conditional distributions of the multinomial distribution, they are binomial. So this is a simple binomial distribution, like if you toss a coin, n times how many successes do you have out of n. And you can calculate the quantiles of the binomial distribution. So you say, what are the numbers, what is the range of values that have, let's say, 99% probability? And you can, because you have a certain precision, right? You can just not consider all the values outside of this range, because they will be very improbable, and then they will be multiplied by other improbable values. So that decays very quickly. And so instead of the whole range, at each step you consider just the most probable one. So at the second step, when you iterate the C's, again, you know how many remaining reads could be assigned theoretically to the C, and that's again the sort of conditional distribution, which is binomial. So again, you calculate the quantiles of the binomial distribution, and at each step this range becomes even smaller and smaller. So that's that should be pretty efficient.
Mm-hmm. Yeah, we actually considered this when we developed this problem, but then we decided to limit our test cases, like size of the tests, to smaller numbers where this optimization are not that required, at least. But if you look, for example, for the real data with large genomes and high coverage, so there you indeed have to use optimizations like this by cutting the tails of the distributions when they become too small. Yeah.
Yeah, sure. I mean, yeah. I analyzed the data that we had, so basically I knew that we don't have too many reads, but your approach is definitely good, and it allows to solve the problem for much larger values. Okay, I think that's very good, of course. But well, this was a qualification round, so I guess it was simplified a bit.
No, absolutely, and I think I'm not that experienced at the contest. I definitely got burned at the first contest, the first bioinformatics contest, which was 2 years ago, where I would just implement a solution to a problem, not necessarily, giving it a lot of thought. And the tests were huge, and it would work for a very long time. So, and when I saw this problem, I knew that there would be like huge, especially since I was imagining like realistic, genome length and realistic. Well, the genome length doesn't matter in this problem, but realistic sort of coverage. And so I immediately jumped into the optimization mode. And I was also curious, like when you are solving a problem, do you just look at the text file, or do you sometimes I would write in my program, I would like create a special mode that would print the statistics. Do you do that, or do you just look at the raw text file to understand what the size of the test is?
If I have the text files, I definitely start by looking at them, and in most cases, you know the size of the input, right? Just the size of the file. Sometimes you need some advanced statistics. If I feel like I need some of them, I definitely build it. But in most cases, it is not needed. Like, it depends on the problem, I guess. But so if there is some non-trivial distribution of, say, nucleotides, then you definitely want to know that, right?
Yeah.
But yeah, so if you need that, then you have to calculate it. If you don't need it, then I just don't waste my time.
So for example, in this problem, did you first implement this simpler solution and it just worked, or did you first ensure that it will work by like looking at the tests?
Yeah, sure. I looked at the cases first, so I just knew that my solution will work.
Mm-hmm. Okay, and the third problem of the qualification round was called Transposable Elements. The author is Ryan Chiki, and the tests are by Maria Atamanova. And in this problem, you are given a genome, this time an actual genome, a sequence, and you have to find a string that appears in the genome at least n times without overlaps. And each occurrence has to have no more than a certain number of errors. So basically, you have to find a repeating motif in a genome where its occurrences are judged up to a certain number of errors, where errors can also be insertions and deletions. Yeah, so it's an interesting problem, also very well motivated biologically, like it's an actual biological problem. And what are your thoughts?
Well, let me first thank Ryan for submitting this problem. So Ryan is a participates in our contest since the beginning. So he submitted this problem, which we are very thankful for. Sadly, we have to use this problem in the qualification round, as Ryan said that he would like to participate in the finals, where he went pretty well. So this problem was suggested by Ryan, and that's why it has pretty nice biological background, and actually, I don't know how to solve it best, so that's probably how to solve it is the question for you, Roman. I believe you solved it, and as all the problems for Gennady.
Yeah, I guess I can start with my approach. Actually, unfortunately, I didn't have enough time during the qualification round to solve this problem, so I just went for the first two, since that was enough for qualification. But then I tried to solve it a bit after the finals, just out of curiosity. And I think I solved 9 test cases out of 10. So, basically what I did was I suppose that our string, the one which we want to find, can actually be a substring of the initial genome. For sure, it is not always the case. So basically, that's why I solved 9 cases out of 10. But in most cases, it is true because, empirically, it seems to be almost correct. But okay, sometimes you have the actual string which you want to find is not present as a substring, but one change applied to it is present at one position, and one change applied to it is present at another position, right?
Mm-hmm.
But if we make the proposition I did, we just can loop over this substring, and then we want to just find its occurrences in the initial string. So we just go through positions, and then we calculate the distance, like the Levenshtein distance,
mm-hmm.
with a simple dynamic programming. Since the strings were short, it was fast enough. Yeah, so basically that's how I did. But maybe you can tell more. I think that actually in the comments I saw that some people were using some bioinformatics software. But yeah, so what did you do?
Okay, and so did you align everything against everything, or so you iterated through the genome, right? So you just took the fixed length part of the genome and then searched for it in other places?
Yeah, that's true. And when I found the answer, I just broke it. It was a bit slow for the larger cases, but with some optimizations, it can be fast enough, so you can wait a bit.
Yeah. So my solution was I started by aligning just everything against everything, and it worked for smaller problems. For bigger problems, I made an optimization which went something like this. So I calculated the k-mer statistics. So I broke the genome into substrings of the fixed length. I think I used like 5 mers maybe. And then you can calculate the density of the k-mer. So basically, at each position, you take the k-mer that starts at that position and calculate how many times it occurs elsewhere in the genome. And so if you have a long stretch of k-mers, each of them occurs the number of times close to the number of occurrences, then that's a likely position. So that was just an optimization to limit the number of strings that I have to compare to all other strings, because that's a quadratic algorithm. Compare everything against everything, and each comparison is also quadratic. And then I have essentially a graph, right? And I can find clicks in this graph. So I can find subgraphs where everything is connected to everything, where the edges correspond to the Levenstein distance above a certain threshold. So basically, if you're allowed to have the number of differences d, then you know that the distance between any two occurrences has to be under 2d, just by the triangle inequality. And so I construct this graph where I threshold the Levenstein distance by 2d. So two strings are connected if their Levenstein distance is under 2d. Then I find clicks in this graph, which are and clicks of the size above our number of occurrences. And then I try to find the the sort of center of this click. And this was the first time, I think, in my life when I applied a genetic algorithm, because generally I'm a bit skeptical of genetic algorithms.
Okay.
But this is a perfect case because we're actually talking about genetics. So this is a good use case. And essentially, what I did was I don't remember all the specifics of what I implemented, but it went something like this. I think I start with maybe one of the strings, and then at each step I compare it with another string, and if they have a big distance, if they have a big difference over d, so it's certainly under 2d, but it could be over d, and if it's between d and 2d, then I sort of randomly recombine them. So I go through this alignment script, right? So if you align to strings, you have a sequence of letters like match or mismatch or insert or delete. And then you can go through the script and randomly apply these changes. So you get a mix of these two strings, right? You have something between the first string and the second string. And I just repeat this many times until I get a solution. So I take the current candidate, I don't remember if I took sort of the farthest or one of the far ones, but I basically recombine the current candidate with an occurrence that is far away from it.
Yeah, that's pretty interesting, I think.
That's cool.
Yeah, that's cool.
Yeah, I think also that when you have the strings and want to find a center, I believe you can use like multiple alignment software that is like frequent in bioinformatics, and there are some online tools that you can try to use. So that probably could solve this last step for you.
I consider that, and I try, but I think even like using an existing algorithm, it could be actually more work. So I considered using Clustal, which is one of the multiple alignment algorithms, one of the popular ones. But then you have first you have to format the input in a way that this algorithm takes, then parse its output. Then you have to deal with like various limitations and assumptions of this algorithm. So, for example, ClassTel is motivated biologically, right? So it assumes a certain evolutionary model of the, for example, DNA or amino acids. So I thought that would be too much work to integrate. But I certainly read up on like various multiple alignment algorithms, and I don't remember whether I actually used any of the ideas, but certainly maybe like took some inspiration from that. I guess my main takeaway was that there's no like an obvious great multiple alignment algorithm. So you have to compose something of your own. For example, for pairwise alignment, there are well-known algorithms, and I just wanted to make sure that I'm not missing one great multiple alignment algorithm.
Yeah, maybe that's a good reason to make some software doing that.
But multiple alignment is an anti-hard problem.
Yeah, that's a problem.
But when you have finding cliques as a part of your solution, which is also anti-hard, so probably one anti-hard plus another anti-hard, two anti-hard.
Minus by minus is not plus, no?
All right, and so that was the qualification round, and now we are approaching the final round, which lasted 24 hours, took place on the 23rd of February, 23rd to 24th of February. And the first problem, I really hope you guys will explain it to me, because I tried to read and understand the problem statement during the round itself, and I failed to understand it. And then while preparing for this podcast, I made a second attempt and I failed again. So I still don't know what is asked in that problem. But it has to do with cancer and chromosome rearrangements. And the author is Sergey Aganezov. And the tests are by Ilya Zban.
Yeah.
So first we're given some background from the cancer biology, which I guess we'll skip. I think a lot of people who listen to this podcast will be familiar with the basics of cancer. But what is the actual problem about?
Yeah. So let me try to explain at least how I understand the problem and why it's kind of complex in the statement. So the problem is about chromosome rearrangements. Well, in particular here it's about cancer rearrangements, but in general this framework is used for all kind of chromosome rearrangements. So there we have, to describe the rearrangement, people use so-called breakpoint graph. There, first you have to describe actual sequence of DNA, and there you have, in this case, in this problem, it described as two vertices connected by an edge, which is called segment edge. So this tightly corresponds to a particular genome sequence. And there, when the chromosome gets rearranged, these parts of the genome, like genome sequence, are getting connected in different ways. And that is represented by adjacency edges that shows which ends of the segments connected to which other ends of the segments. And in this case, these rearrangements that are considered they're not just shuffling of the genome, but also can include multiplication, like amplification of the parts. So that's why we have a lot of the adjacent edges. So for one particular genome segment can be connected to multiple genome segments. And when you have this rearrangement happen in real life, for example in cancer, what you can measure by sequencing is actually what segments are connected to what segments. So when you have normally you have a linear DNA in multiple chromosomes, and when you have normal genome, you sequence it, you align it to the reference, and everything aligns perfectly. But when you have these rearrangements happening, your DNA reads will be aligned to, like, one particular read can be aligned to different parts of the genome. So that's where these adjacency edges are coming from. And the question of the problem was basically after having the genome sequenced, like cancer genome sequenced, you have this data, which was kind of pre-processed for the participants. So basically, after this pre-processing, and what was the input for the problem is which genome segments are connected to which other genome segments. And the question that we asked was to find. So as we know, that after all this rearrangement, it's still a number of linear or maybe circular chromosomes. So the question was, though there was two types of question in this problem. One of them was to actually describe any of the possible rearrangements that is consistent with the data, with the input data. And the second question, like more hard, was find the minimal number of chromosomes in the decomposition. The part that we didn't ask was to find the maximize the number of chromosomes in decomposition, which is also an interesting problem, but it's harder. But in general, that was to find what would be the simplest genome, when simplest is the number of chromosomes, that is consistent with the data, with the input data.
And so in this graph, the vertices correspond to the ends of the original segments?
The vertices correspond to the ends of the genome segments. Like basically each position in the genome can be described as a vertex, or actually...
But not each, because you have like a whole segment, right? It corresponds just to two vertices?
Yeah, but here we considered only the like nucleotides that are adjacent to the actual breakpoint in the chromosome.
Mm-hmm.
So that's why it's limited here. But actually you can, in the like infinite case, and each nucleotide would be a vertex, and they will be connected if there is a like linear genome segment that has both these nucleotides.
And so there are two types of edges. So there's a segment edge and adjacency edge. So what are those?
Yeah, so basically the segment edge is corresponds to a genome sequence. So on it you can write some letters of like A, T, G, C, and so on. And adjacency edge basically so you can consider it as like a puzzle, where each segment edge corresponds to a piece of a puzzle,
mm-hmm.
and the adjacency edge describes which of the puzzle pieces can be connected with each other puzzle pieces.
Got it. So the segment edge connects the left end of the segment with the right end of the segment, and the adjacency edge connects the right end of the segment with the left end of the next segment.
Yeah.
Right. And so once you read this problem statement and understand it and do some thinking, can you reduce this to like a simple problem on the graphs?
Yeah.
Is this like a standard problem?
I think it's not standard. I haven't met such a problem in programming competitions, so you can't say it's standard, I think. But yeah, it's some kind of graph problem. So basically, if we just talk in terms of graphs, we have an undirected graph with, vertices, edges. Each edge connects to vertices, and the edges are of two types. The first type and the second type, but let me call them that way. And we want to decompose this graph into a collection of paths and cycles. And we want cycles to consist of edges of the first and second type alternately. So that you have first, second. So every cycle must have an even number of edges. And we want paths to consist of alternate edges as well. First, second. And we want paths to start with the first and end with the first. Okay?
Right.
Yeah. So that's what we want to do. I guess I should just talk about the solution. It is not too hard, I think. So the idea is, the first idea is that each vertex, the number of edges of the first type adjacent, incident to a vertex is at least the number of edges of the second type incident to that vertex. Because for each cycle, each vertex in the cycle has one edge of the first type and one edge of the second type incident to it. And on a path, each inner vertex has one edge of the first type and one edge of the second type incident to it, and the ends of the path have just one edge of the first type, but no edge of the second type. So each vertex has the number of edges of the first type is not less than the number of edges of the second type, right? So if this condition is not satisfied for some vertex, then we know that there's no answer. There's actually a case in the problem, so we have to output yes or no. So the case of no is when some vertex has too many edges of the second type incident to it. Okay, so the second step is for each vertex, if it has too many incident edges of the first type, okay, let's just fix it. Let's collect all vertices along with multiplicity. So suppose some vertex has two extra edges of the first type, let's say vertex A. Let's say vertex B has one extra edge of the first type, and let's say vertex C has also one extra edge of the first type. Then what we will do is we will create new fake edges of the second type. In this example, we'll connect A to B with an edge of the second type and A to C. So if we do that, now every vertex has the same number of edges of the first and second type instantly. Okay, and we can always do that. This kind of simplifies the problem. So if we know that, okay, so now let's proceed to the case when every vertex has equal number of edges of the first and second type incident to it.
But this works if there are just two vertices or if there's any even number, because then you have to consider like how to pair them, right?
Yeah. Basically it doesn't matter how you pair them. What matters is that, you can have any number of such vertices, in fact. So, and you can just connect them in any way. It doesn't matter.
Right. So you'll create new cycles, but they will consist of some number of like linear segments or linear paths. Right?
Yeah.
So you're just connecting these paths randomly.
Basically,
and forming cycles.
Yeah, that's true. So I will connect. Right. I create new edges and then I decompose the graph into cycles. And then I just remove the edges which I added. And this way the cycles break into paths. Some of the cycles do not break if they don't contain any new edges, but in most cases, a cycle contains some newly created edges. When we remove them, then we have paths, right?
Mm-hmm.
Yeah. So, and how to create the cycles? What you can do is actually just pick any vertex and just go from it. Use an edge of the first type. Then from the next vertex, pick any edge of the second type, and so on. And so you just alternate the edges. And then, when you enter a vertex, so you mark the edge as used when you use an edge. Okay. When you move along an edge, you mark it as used. And so you enter a vertex and you exit it using an edge of another type. And so since every vertex has equal number of edges of the first and second type incident, you're guaranteed that when you enter a vertex, you will be able to move out of it. So you just go from some vertex until you run into a vertex which you visited before. And if you do that, then you have a cycle. You just remove the cycle and continue. So this way you can get a cycle decomposition of the graph.
Yeah, so that's like the standard sort of Eulerian cycle.
Actually, I'm not sure. I was trying to do something with Eulerian cycle, but it's a bit hard to alternate the edges in the Eulerian cycle because you can't guarantee that. I was actually struggling with this problem quite a bit. I spent quite a lot of time on it. So, but yeah, what I eventually did was just build cycles of, like, just build some cycles, not necessarily Eulerian ones. And then when I had several cycles which had a common vertex, I connected them into one cycle. So that if you have a vertex and two cycles passing through it, you can connect them into one cycle, right? And so I did that until I have the minimal number of cycles.
So the hard part is just minimizing, but decomposing into some kind of decomposition, is it straightforward? Is it just what you described?
I think so. I think that it is similar to Eulerian pass, Eulerian cycle, but here we have two types of edges, right? So that's what makes the problem different from the standard one, right? If you just had one type of edges, then you just find the cycle which passes through all of them and you're done. But in this problem, you have to alternate the edges. Maybe you can just modify the standard algorithm to account for that.
All right, so the second problem of the final round is called Epigenomic Marks. The author is German Demidov, and the tests are by Artyom Vasilyev. And I really, really like this problem. It is quite realistic, right? It is also very, very simple to understand. So you are given several tracks of epigenomic marks, which are basically bits. So a mark is either present or not. And a mark could be, I guess, something like DNA methylation or some histone. Well, it doesn't ideally map to a biological concept because the histone modification is obviously a property of the histone, but you could superimpose something like a histone modification track on top of the DNA track. And so you get several tracks of this epigenetic marks. And you have to sort of cluster them into a smaller or small number of different states. So the states could be, for example, open chromatin, closed chromatin, or something like that. You don't have to name them. You have to simply classify, simply assign to each locus in your genome to one of the states. And the score is just the entropy, the total entropy. So given the first state, so you consider all the sites that were assigned to the first state, and you calculate the entropy of this conditional distribution. So so conditional on the state, we can observe a certain distribution in the first track, a certain distribution in the second track. So you compute this total entropy, and you have to minimize this total entropy. And so the problem is relatively easy to understand, but I found it pretty hard to solve. So what do you guys think?
Well, first of all, it's actually due to our mistake. It was pretty easy to solve. Well, not completely, but to a pretty good degree. So basically, the trivial solution of putting all the zeros gets a very high score, because
so assigning everything to a single state?
Yeah, because in the initial states, the initial marks are not uniform, so are not 50-50 distributed. Usually there are a smaller number of ones and then number of zeros. So basically, just assigning everything to the single state gets you a pretty nice score.
So the entropies, they just add up, right? So do you sort of minimize the total entropy by just considering not like 10 distributions, but just one distribution? Is that the idea?
Yeah. I think that it's just that you have an entropy which is accumulated over all states. And if you assign it randomly to k states, then you have approximately k times what you get if you just assign everything to one state.
Right. That's interesting, because intuitively you actually want a larger number of states, because then you can sort of more precisely match them to the profiles.
I think that this issue could be easily fixed if the baseline score was not generated by a random choice, but generated by assigning everything to one state. So you have actually to improve that.
So, Gena, what was your solution? Did you just put all the zeros?
In fact, this problem had 4 test cases. The first one was pretty small. The second one was a bit larger. And the third and fourth one were the biggest ones. And it was a bit interesting that the bigger cases were simpler to solve than the smaller ones. Because for bigger cases, you had bigger number of states, and then just setting all zeros gave you even more score. So it was actually quite hard to improve over the baseline, like this kind of baseline solution for the larger cases. And so I didn't do exactly that. What I did was some kind of, I have you can call it local optimizations. So I'm not sure how to call it. So it's a bit similar to, like, what you can do, for example, is simulated annealing. Or you can probably do genetic algorithm as well. So what I did was just, you have a string of length L, which consists of numbers from 0 to k-1, and then you can apply some kind of mutations and maybe recombinations and recalculate the entropy. And if it improves, then you can keep the state. If it doesn't improve, then you can roll back and so on. And that's what I did. You can do something more difficult, more involved. And it was a bit sad that the scoring was not very good. So it didn't motivate you to investigate more time to this problem, because just simple searches gave you quite good score. But anyway, I think that I had the close to best scores on the first and second case. So yeah, but it gave me 4 points, I think.
Yeah, I think I considered some variation of local search, like simulated annealing, but I didn't really get around to implementing it. I think one of the first things I tried is just some kind of naive clustering. This was the only problem. So normally I use Haskell to solve these problems, but this was the only problem where I didn't even bother with the Haskell solution. I just I spun up R and I read the tests into R, and I just played with them in R. And the first thing I tried is just simple clustering. It didn't work. I was a bit surprised, to be honest, that it didn't work that well, because intuitively that's what you want to do, right? You want to cluster these states together. And my second attempt, which worked relatively well for smaller cases, it didn't work at all for larger cases. But for smaller cases, what you could do is just to go through the loci in order, just to consider them one by one. And for each locus, you look at the existing distributions, and you just choose the state one of those k states where to assign this locus to minimize the current entropy. And then if you have enough time, you can do several iterations. And I think this worked for smaller test cases, but for larger ones, I couldn't even complete a single iteration. And it's also interesting. I was thinking how to apply some not discrete optimization, but somehow apply the proper optimization, because you're optimizing the entropy, right? It's a nice smooth function, and how to convert the gradient of the entropy into the original assignment. But I didn't come up with anything. But it seems that this problem should have a proper solution. First of all, this problem is so simple to formulate that it's hard to believe that it hasn't been studied before. There has to be some kind of canonical algorithm, right?
Well, for this problem, so similar problem, there is a tool called Chromosome, which is based on hidden Markov models. So our idea was that this problem can be solved with this hidden Markov models algorithms, where you have to train your model, and then the state of this model will be the state in the output.
But what would be the transitions between the states?
So idea was to mark each genome position with a state, and from each state you can get to any other state. So all the transition probabilities are probably maybe uniform, but so like it's connected pairwise. But what you have to find is how do you assign states to each of the position, and what the probabilities of, so how the state looks like. So what the probability of getting each epigenomic mark is at each state. So that's how. So basically, for this problem can be solved in terms of hidden Markov models, where you develop model. So basically, for each state is just a distribution is a probability distribution of getting each of the marks.
Yeah, I don't know. The hidden Markov model doesn't seem like a great tool here, exactly because there is no obvious interpretation to transition between the states, right? So
yeah, but it's not about transition; it's about states, and basically, transitions are not that important here.
Exactly, that's what I'm saying, and that's why it's probably like the hidden Markov model is the wrong model here. Exactly, because the transitions between the hidden states is an important feature of an HMM, and if you're not using that, maybe that's just the wrong abstraction. I'm not saying the algorithm is not good, but maybe that's just the wrong way to express it.
Yeah, but we never know. And for the people who are listening to this podcast, so I guess we'll try to make this problem into the next qualification round with a proper scoring. So this is
do your homework.
Like kind of a spoiler.
Yeah, but I'm surprised that there is no. So I would expect there to be, when I said like a canonical algorithm, like not basically an HMM or something like that, is just a heuristic or like a more
like for HMM.
problem, but
for HMM, there is I guess it's called a Viterbi algorithm.
Yeah.
So there is one particular algorithm that optimizes it. So that's kind of well-defined solution. While the model can be like not exactly the one that should be used, but for this particular model, there is an exact solution.
Yeah, the Viterbi algorithm works for an HMM, but then the mapping from this problem to HMM is sort of imperfect. But I was talking about like the precise, the exact solution to this problem, because how do you minimize the entropy with a limited number of states? Like the problem just seems so simple that someone had to consider it. Maybe we should ask German. Do you know? Did he tell you how he came up with this, or like?
So actually, it's the other way around. So when we discussed this problem with him, so his idea was that the HMM is slow for a big number of marks and big genomes. So because this problem is very biologically relevant, so we are indeed using chip sequencing data or methylation sequencing data. You can get these marks and get these genome tracks, and then annotation with the states is kind of time-consuming process, a computationally time-consuming process.
Mm-hmm.
And so his take was to get this problem solved by someone, and so to get the better algorithm for this. So I guess we'll have to wait another year for this to happen.
Yeah, in that case, it's more appropriate for the qualification round when you have the whole week and not that many problems to solve. But also, the fact that you try to minimize the entropy, is that the goal in biology as well? Like, it's not obvious to me.
Well,
it's a very nice scoring function, but I don't know how biologically relevant it is.
And like I said, in biology, you don't know exactly what you want to optimize.
Yeah.
So this is just one particular way to score it. That kind of makes sense, but maybe not the biological one.
Yeah. It's a very nice problem. And the next problem is bacterial communities. And I should say it is by Nikita Alexeyev and Mikhail Raiko. And the tests are by Vitaly Demenyuk. And in this problem, you're given some samples from many generations of bacteria. So you start with a single bacterium, and its genome has a fixed length, and the genomes of all the subsequent populations are of the same length. So at each generation, you subsample from the previous one, and you make some point mutations. There are no insertions or deletions, just point changes. And from each, first of all, you're not given all the generations. You're given only some subset of generations. And from each generation, you're also not given the full, all the organisms, all the genomes from that generation. You're again given some random subset. And you have to order them by their evolutionary age. So which generation was earlier and which one was later.
Yeah, so with this problem, the hard part was to find the proper formulation around this general idea of evolution and finding which samples are closer to which communities closer to which other community. So we had several ideas how that can be formulated as a problem. So maybe the one that we end up with was not the ideal one, but well, that's what we ended up with. And yeah, there we just described a pretty formal. So we gave a pretty formal description of the simulation of the process that we used to simulate the evolution, and then you have to solve it somehow. And so for this problem, so we don't know the solution. We don't know how to solve it to 100%, and I believe actually it can't be done.
Yeah.
So
it's just too little information.
Yeah, and what I really like about this problem is that Gennady doesn't have the best score for this problem.
Oh, really?
Actually, There is a participant.
Oh yeah, I see. Victoria Kobets.
Yeah, Victoria Kobets, who solved it better in the last test, and actually it's even better than. It's also better than the solution that we have.
Yeah. Oh well. I'm not going to be shy, and actually I got a better score after the contest. Well, anyway, in my opinion, this problem is the most exciting of all the problems of the qualification, the final round at all. So, what I liked is on one hand, you have a very formal description of the process, right? So, you know how the data is generated, but on the other hand, it's hard to extract information from the input you get. And I think that you have, you can actually infer a lot from what you're given, but the hard part is to actually understand how to do that. And I feel like there must be a lot of ways to do that. And my intuition is that a perfect solution is possible for the given cases, at least. Because, of course, in fact, what you are given is some subset of generations and some subset of genomes from each generation. So, of course, if you're given 2 generations and 1 genome from each, you can't do much. But if you're given some significant part, I think that it should be possible to do quite well.
We should clarify what does it mean to have a perfect solution. So one interpretation is that a solution is perfect if you can actually exactly reproduce the original order, right? But the other interpretation is that there is some kind of probability distribution on all possible orderings, even though it's not efficiently computable, but the perfect solution would find the most probable ordering given the data, which if you have little enough data, it may not coincide with the original ordering, I suppose.
Yeah, I think that's reasonable.
Are you saying that there should be a solution that is always able to reconstruct the original ordering given sort of a reasonable amount of data?
I think that probably the most probable solution is hard to find. I think that, I guess you can do it, but in a lot of time, right? But I think that for really small cases, you can find the most probable solution. But for a bit larger cases, of course, I think that you shouldn't be able to do that. But what I was saying is that I think that in the test data given, the amount of information is not so low. So in fact, okay, what I was actually saying is that I think that you can still do much better than what the competitor did. I feel so, but well, maybe I'm wrong.
So
but I feel like there are a lot of sources of information. Yeah, sure. So there were two approaches, I think. One of the approaches is to note that the first generation consists of just one genome, and all generations are generated from the initial genome. So it is reasonable to think that the earlier generations consist of more similar genomes.
Yeah.
Right? So what we can do is, for each position in the genome, find the distribution of nucleotides on this position. And for example, or we can find the frequency of the most frequent one on every position and sum it up over all positions. And it will be some kind of measure how similar are the genomes in this generation. Okay, so just for each position, we just find how different are the nucleotides in this position. And then we can just sort the generations according to this matrix. And
so sort of sort by variance, right?
Yeah, kind of. I guess that variance is the correct term for this. Yes. So you can do it by variance. Yes. So you just take into account that the earlier generations are more similar. Yeah. I think that this approach gets some score, but it's not good. It's not too good. But I think that that's what most competitors did. From the scores, when I tried some kind of approach like this, I got similar scores to what most people had.
Yeah, I did something similar. So my first approach was to calculate the consensus sequence. So to put together all the genomes from all the generations and at each position to find the most frequent nucleotide. And this gives you the consensus sequence. And then you just order the generations by how far they are from this consensus sequence. And so that was like literally the first thing I came up with. And then I was coming up with this more sophisticated, like as you say, sort by variance. It was very frustrating that they weren't working better than my first approach. So when I tried to sort by variance, or I also tried to sort by some combination of variance and the distance from the consensus, it was actually doing worse than just the simple distance to the consensus, and I couldn't improve on it.
Okay, I see.
Didn't have any other ideas.
Yeah, sure. Let me talk about the second approach I had. So this one was actually the better one. It's close to what I eventually did. So the idea is that our solution, which just calculates variance, doesn't compare generations to each other, but it just calculates some statistics for each generation. It's not good enough, but what we can do is, for example, like the simplest way is take two generations and find the number of common genomes in these generations. And this will be a kind of a matrix how close these generations are.
Mm-hmm.
Okay? And then what we can do is something like this. We start with some generation, like as the first generation in the output, we can take the one with the least variance, but then each next generation is picked as follows. We can pick the generation which is as close to those which are already output as possible. So basically, for example, for each pair of generations, we calculate distance between them, or probably not. Not distance, should be called like similarity, the number of common genomes. And then when we have some prefix of the output.
Oh, okay. So you're not looking at the nucleotide-wise distance.
Basically, but... Basically, you just find the equal genomes. But
right.
That's what I did. Yes, you just calculate equal genomes. Okay,
I see.
And then you just find, given the prefix of the sequence, you want to find the next element, and this one will be the one which has the most common genomes with the prefix, and you just put it there, and then find the next one, and so on. And this approach doesn't account for nucleotides at all. It just compares genomes, and they should be exactly equal. And it's already good enough to score a lot of points, but of course, instead of comparing them strictly, you can compare, like, if the genomes are similar, then it's also like, it's not 1 point, for example, but 0.9 or something like that. And basically, like, what I did was strict comparison, but again, I think that you can do better here. So yeah, basically the idea is to if you have enough generations from the whole set, then you just compare generations between each other.
Right. And Alexey, of course, you didn't have to solve this problem because you already had the inside knowledge of the perfect solution. But what was the best thing you came up with?
Well, so our jury solutions was generated by Vitaly Demyanuk, and I guess it sounds very similar to what Gennady has. So it's also actually the sorting by first like variants and like in general how they far from the origin is indeed the first solution that makes the simplest solution to solve to use for this problem, and it indeed gets you kind of nice points. Yeah, but in general you have to compare generation pairwise and then somehow select the sequence in which you want to trace this. This greedy approach can be used, like similar to what Gennady has, but I believe Vitaly also did some, like after the greedy approach, you can use some local optimization techniques to make it even better, like to slightly switch the order of the, like local order of the generations.
But what is your sort of scoring function when you do optimization?
Yeah, like basically distance nucleotide wise, or I believe nucleotide wise distance between the sequences in the generations.
Yeah, so basically the question is if you can compare two generations, which one came earlier, then that's what you want. I actually thought about that. Well, I didn't have time to implement it, but I think that's the next thing I would do. I would try to compare two generations. I'm not sure if it can be done efficiently. When you do some kind of local search here, you don't actually need some kind of scoring function, right? I mean, if you just can compare two generations, you're fine. But, well, I'm not sure how to do that efficiently. So when we make the next generation from the previous one, we create some additional copies of genomes, right? So we replicate some genomes and then we remove some random genomes. So the next generation will have some repeated genomes from the previous one. So maybe if you have some genome which appears one time in one genome and two times in the other genome, then the other genome is more likely to come after the first one, right?
Oh, that's a good idea. Yeah.
Maybe that some kind of along these lines we can do.
Also, somehow in this contest, a lot of times I saw a ghost of the traveling salesman problem. Like here, you want a linear ordering of everything, right? So that the sort of total path is minimized.
Yeah, that's what I actually tried to do first. Like I said, I found the similarity function between two generations, which was just the number of common genomes, and then I tried to find the best path in this graph. But it is not good enough because you not only you want the adjacent generations in the path to be similar, you also want those which are close in the path to be similar as well. right? So you want the distances to be like, I mean, it's a bit harder than traveling salesman, I think. So that's why the first attempt was to find, like, when I had some prefix, I wanted the next generation to be as close as possible to the last one in the past, in the prefix. That's what I tried first, and it didn't do well. But when I found how similar it is to all the generations in the prefix, then it was very good.
And actually, I just checked what Vitaly's solutions are getting, and the scores are pretty similar to what Gennady has. So we can't really solve it much better.
Yeah, anyway, I think that it was a very interesting problem, so I enjoyed it a lot.
Gennady, I also wanted to ask you, what language are you using in these competitions?
I use C++. Basically, the idea is that in programming competitions, you kind of have to use C++. It's not obligatory, but most competitions, like most participants, use C++ or Java. The other languages are not widely supported, and the problem is that in most cases they are slower, and the traditional algorithmic and programming competitions, they are revolving around the complexity of algorithms, but you also have the implementation to be efficient enough. And that's why we want to have an efficient language. And sure. For example, for the last few years, Python is becoming more and more widespread in programming competitions. But in problems where efficiency is important, you usually don't go with Python. You go with C++ or Java. And so C++ is kind of the standard choice for the competitive programmers.
Yeah, it's a good balance between the raw efficiency, but also availability of some like basic algorithms. So I assume you can use STL, right?
Yes, of course. And so it's high level enough, but it's efficient enough as well.
Are you allowed to use Boost?
No, Boost is usually not allowed.
Right. All right, 2 problems to go. So problem number 4 is minimal genome. And that's another great problem in the sense that it's very simple and, very simple to understand, very hard to solve. The problem is by Vitaly Aksionov, and the tests are also by him. So the problem, I love this. It's literally 2 lines of text. I'll just read it verbatim. You're given a list of proteins. Each protein is represented as a sequence of amino acids. You have to find as short DNA sequence as possible from which all the proteins can be translated. So that's basically it. You have to find a DNA sequence where, like, depending where you start, in which direction, you translate proteins according to the standard genetic code, and you have to generate all the given proteins, right? And I sort of thought about the parallel between this and genome assembly, except when you assemble a genome, on the one hand, you don't have this variability because each amino acid, of course, corresponds to multiple codons. And so there's an extra degree of freedom here. On the other hand, this is more exact because there are no errors. So this has to match exactly. And I was thinking about applying some genome assembly algorithms like the De Bruijn graph to this problem, but I didn't succeed. So what do you guys think?
First of all, from our side, we didn't know how to solve it, and it was pretty nice that this problem was solved completely to the full score. So Vitaly till the end was kind of curious if it will be solved or not. So it was really nice that it was solved actually.
Mm-hmm.
Yeah, I guess you didn't have to know how to solve it, right?
Yeah, but that's our why it's good to be a jury, so you don't have to solve it actually. That's a problem of participants.
Yeah, just pose a problem and then let participants show themselves.
Also, it's another problem where if you squint, you can see a traveling salesman problem, right? Because if you find overlaps between the proteins and then you sort of try to traverse this, except you have to ensure that the overlaps are consistent, because different overlaps can assume different codons for the same amino acids.
Yeah, that's true. But yeah, okay, so I can tell what I did. What I did was the core of the algorithm was greedy. So if you can find two proteins which align well, you can just join them into one string.
How do you efficiently find overlaps between proteins? Do you like consider all the overlappings, or do you use seed and extend, or what do you do?
Sure. So I actually tried all overlappings. Yeah, the first problem you encounter, well, when solving this problem is that every amino acid can be represented in different ways, right?
Mm-hmm.
So that's quite difficult because you just don't know if it will match or not. What I did some kind of simplification of this problem. For each amino acid, I just considered all its codons possible. I'm sorry, I'm not sure if I'm using the right terms because I'm not much into the biological part, but I guess you will forgive me. So each amino acid is represented as a string of 3 nucleotides, right?
Mm-hmm.
And we have several representations, but some nucleotides are fixed, are the same in all representations. So if some nucleotide is fixed, then I just use it in this position because I know it is fixed. And if some nucleotide is not fixed, I just replace it with an asterisk because I don't know this nucleotide. It can be, even if it can be just one of two, I just replace it with an asterisk for simplicity.
Right.
Eventually, that's how I translated the strings of amino acids into the strings of nucleotides and some wildcards. And then I just tried all possible intersections, all possible overlappings of two strings. And so if I have some overlapping, I just made sure that in the intersection part, all characters match exactly. So if I have wildcard against a character, it's okay. If I have a wildcard against a wildcard, it's okay as well, of course. And if I have a character against another character, a different character, then this overlap is false. It's not what I can use. And then if I had some strings which overlapped enough, I mean, if the length of overlap was at least 10% of their length, for example, I assumed that this cannot be a coincidence and you can just merge them into one string. So basically that was it. I was just looking over pairs of strings and try to align them.
Interesting. But 10% only over the positions where you know both letters, right? You don't consider asterisks.
I just said that if I have, I think it was just of 10% of the whole length.
Okay.
It doesn't matter too much here. And 10% is just like a random number. You can replace it with someone. If you cannot assemble it into one string, then you want a lower number there, right?
Mm-hmm.
And if you have some false positives, you want a higher number. So you can just do that manually, fix this number. And the interesting part is that actually I solved the more difficult cases fully, but I couldn't solve a small case fully. Like of all 6 test cases, I solved test case 6, but I couldn't solve test case 5, which was the same, but the length was 200 and not 100,000. And that's a consequence of the way of solving I chose, because when the strings are short, there are a lot of asterisks. It's hard to find the balance between matching and not matching so that you don't have false positives and false negatives. When you have long strings, if you have a very large overlap, then you can be sure that you just have to merge the strings. And in case of short strings, it might be false. So yeah, basically that was my trouble. But it
Nice.
solves the problem pretty well for large strings. So yeah, I guess.
Yeah, you got almost full score for,
yeah, I got
for that.
almost full. Yeah.
Pretty cool. All right, and the final problem is endangered species. So this problem is by Alexey, and the idea is that you have the species E. spherica, and you have N males and N females, and you have to pair them in such a way that ensures the maximal number of heterozygous loci. So you're given the genotypes of the diploid genotypes of each individual, and you have to pair them in such a way that you get you maximize the number of heterozygous loci. So Alexey, how did you come up with this?
Well, this is kind of continuation of the problem from the second contest.
Yeah,
where
the breeding problem.
Yeah, the breeding problem.
Cow breeding.
Where you had to breed, cross the cows to breed a better milk producing cows. So basically so there was ideas of using the similar backend or similar model, but from the different perspective. So in the second contest, the problem was the genotypes was not known. So people have to optimize the milk production based on different other qualities.
Yeah, you had to rely just on the phenotypes.
Yeah, but here we had the genotypes, and we want to conserve these animals and to get it as heterozygous as possible. And we tried again to make multiple formulation of the problem. And what was curious, what was unexpected for me, that actually, initially we tried to pose this problem as how to make the number of potential genotypes in potential alleles in the population as maximal as possible, so that basically for each so the idea was that for each position that can be heterozygous, you want to keep it heterozygous. But what was unexpected for me is that it doesn't matter how you cross the population, the expected number of positions that will be heterozygous in general population will be the same. And from that we had to switch to this formulation when we have to optimize the number of heterozygotes inside each particular individual. So here we have two parts. So first we have genotypes, but we also have a recombination model that allows you to tell how the genome position are correlated with each other in the offspring compared to your initial generation. And yeah, so it's kind of similar to a best matching problem, but with a nice twist of randomness. And, so I guess Gennady can tell how he solved it, and I guess it's more or less what we expected it to be.
Well, of course I will tell that. Yet again, the recombination model was mentioned in the problem, so it told you the probability of recombination between two positions on the same chromosome. But, at least from my point of view, is during the contest, I think that it doesn't matter again. And I think that, again, regardless of how recombination takes place, the expected number of positions you're looking for doesn't depend on the recombination model. How do you think? Do you think it's false?
No, actually, the expected number of based on the genotypes, what you can do, and I guess that's how Gennady solved it. At least part of the solution is that from given two genotypes of like one male, one female, you can find the expected number of heterozygotes in the offspring. And this is a like exact number, and it indeed doesn't depend on recombination. So it only depends on the genotypes in the corresponding position.
Yeah, exactly.
And from that you can get a like matching with a maximal score, with maximal expected number.
Yeah, this is the standard assignment problem, which can be solved, for example, with Hungarian algorithm or some kind of minimum cost maximum flow. But yeah, so this allows you to find the best pairing on expectation, right? But the problem asked you to find the pairing which is above, which generates at least some number of positions, of good positions, right? To get the full score.
Yeah.
And, well, it was a bit weird because if you want your number of heterozygous positions to be above some threshold, you obviously, like in most cases, you want to take the best on expectation because there's some random process. So it's reasonable to want the best on expectation pairing, but apparently it was not the case. Like if you just do the best pairing, you didn't get the full score. It was a bit weird. I think that you should. It feels like you should.
Well,
and basically, the thing was that the random number generator seed was fixed. So with the same pairing, you always got the same number of positions. But if it was not fixed, I guess that if you just submitted the same best on expectation pairing enough times, you would get accepted at some point.
Yeah, so our idea was that what recombination model influences is dispersion, like variance of the number of heterozygote positions. So idea was that, and actually, so basically, you want to find a number of pairings or like assignments with a high probability of getting the full score, of getting a number of.
Yeah, okay. Variance is actually interesting. So yeah, so do you want to get pairings with higher variance or lower variance?
So you want, like if you look at, some particular test case, like you want to get like 320 heterozygote position. So what you probably want to maximize is to maximize the probability of getting more than 320.
Yeah, okay.
And
yeah, that's reasonable.
So the number of the submissions that you are making is not that high. So basically, the idea was that people can try to optimize, for example, expectation plus the one variance, like one sigma, and get something around, and get the solutions around this value, like around this maximal value of expectation plus variance
with high probability. Yeah, okay, that's interesting.
Yeah,
but what I actually did was just generate several, like you said, I guess I generated several good pairings and tried to combine them and to maximize the score.
So I guess the trade-off in this problem was a number of submissions that you are making.
Yeah, I think that it should have been limited, at least time wise, so that you can't make too many, like for example, you can make at most one submission every 5 minutes or something like that, because otherwise you just can spam with different pairings and hope for the best.
Yeah, but it still takes time, so.
It takes time, yeah, so that it's still a trade-off, yeah.
Yeah, so I don't know, like, what is better, just to submit many solutions or find a slightly better algorithm and submit smaller number of submissions.
Or spend some time to write a script that automatically submits random pairings.
Is it allowed? Are there any rules against it?
Well, there are no rules against it, at least at the moment. So
are there any rules at all? Okay.
Yeah, and actually.
Oh, there are some rules. Yeah. Honor of code, right?
Yeah. Yeah, but for example, I guess for bacterial communities, you can use the number of transversions that are reported
Inversions, yeah.
to somehow optimize it a bit.
Yeah, I
to
think
your
that if you have
solution.
a script, you can actually optimize it to full score.
Yeah, so this is actually allowed, for now at least.
But yeah, I'm not sure how to write scripts. Do you have some API for Stepic?
Yeah, I guess there is nothing yet. So at the point when there will be a Stepic API, probably will be disallowed.
Yeah, I think as long as they don't have an explicit CAPTCHA or some kind of bot prevention, then it shouldn't be hard just to reuse the authentication cookies.
Yeah.
All right, guys, we'll have to wrap this up. This has been fascinating. I really appreciate your time and, being able to peek inside the minds of the organizer and the winner of the contest. So thank you, and I hope we'll meet at the next contest. I hope it will happen.
Yeah, of course. I hope it will happen too, because as I said, I was very interested in the problems. So I hope to see some more of them.
Yep, keep it up.
Yeah, and as an organizer, I can say that, well, we'll try to make it. Yep. So thank you, Roman, for hosting us.
Yeah, thanks a lot, Roman.